It's just fun to instigate. I will begin with a word of prayer. Heavenly Father, we thank you for this day, and I just pray that you help us to understand what it is we're talking about today, and homology, and in the name of prayer, Lord Jesus. Amen. Alright, so we got ourselves into this much trouble. We have defined the singular n-chains as sums of sums of continuous maps of standard n simplices into some topological space. And we defined this boundary operator last time, and after some combinatorial jibber-jabber, we proved that the boundary squared was 0, which gave us, among other things, the notion that there are these boundary cycles, and there are n boundaries and there are n cycles. Every n boundary, because it's the image under the boundary operator, is automatically an n cycle because partial squared is 0, whereas of course not every n cycle is necessarily a boundary. And that's where the topology is. And that, in a nutshell, is captured in these homology groups, this HNX, which are formed from the quotient of the n cycles by the n boundaries. So this is exactly what you need to find those n cycles, which are not just n boundaries. Whatever's left over in this quotient is what's interesting topologically. And so a little bit of notation that we'll be fighting with today. A homology class, right? Two n-chains, I suppose. What do I want to call these things? N-cycles? I don't want to say n-cycle. What are the stupid things called? I guess they're n-cycles. No, n-cycles presupposes they're in the kernel, that's not what I want to say. They're, let's say n-chains, for lack of a better term. I'm sure it'll hit me later what I'm supposed to be saying right now, or that I'm supposed to be saying this and I'm an idiot for quibbling over it, but whatever. Anyway, so you take an n-chain plus the set of all n boundaries. This gives you the homology class. Two n-chains which are in this equivalence class are said to be homologous, and that's the kind of thing we have to do calculations in. Everything we do in this world kind of has to be shown to be independent of the choice of representative, right, in these cosets. These are additive cosets, so they're right, not too bad. All right, where was I? Our next aim is to show that Hn is actually a functor, right? So let's see here, what are we going to do? Yep. It's cool. I'm going to need to get out my eraser. Soprano claims that he's not supposed to be at bed rest right now, but I don't entirely believe him. I feel like if you go to the hospital and have a procedure and you're on antibiotics waiting to have another surgery, odds are you've been told to go to bed rest. That's my theory, and I'm sticking to it. But he claims
he still has another
he claims
surgery.
he was not told.
What other surgery does he have?
I think he has to have an organ removed or something. I don't know. Not sure exactly.
He didn't get it removed in the first surgery.
No. They're just. You can ask him for the technical details.
There's his kidney too.
Oh, really?
No.
Okay.
It's like. I know he is obviously an advocate of bachelor living. He's makes a powerful argument for it against the evils of women and so forth, and in large part understandable. Not personally, but I understand. I mean, there are evil women in the world, and if you have suffered the wake of one, these feelings are understandable. But I feel like if there was a woman in the equation, you would be resting. I know, I wouldn't be teaching.
Yeah.
As I'm... Well, anyway, let me continue teaching with my pneumonia. Let's see here. Or whatever it is I have. Sure, it's not contagious. Anyway, this is such a large room, you're probably fine. Let's see here, where was I? Oh yes, functor. We need to define, right, So we look at a continuous map, F, topological space, X to a topological space Y. And we look at our singular n simplex, which is what? Just a continuous mapping from the n simplex to X, right? And what do we want to do? F composed with sigma is what? That's going to be mapping from here to here to here, right? So it seems like that's a natural candidate for having a singular n simplex and Y, right? He says extending by linearity gives a homomorphism. So we're going to define a homomorphism, which he denotes by F sub sharp. So here you go. How do you define it? Take a sum of I keep forgetting words here. Here's a particular singular n simplex, right? No, that's not it.
Well,
This
it's
is,
not just that because it's linear combinations. Of
right,
it.
so it's this is a singular n chain, right?
Right.
So an arbitrary linear combination, integer linear combination of these, right? And, oh, well, I think even I could have thought of this. So there you go. That would be the definition. Extend linearly, that gives us a homomorphism from singular n chains of X to the singular n chains of Y. Right? He says this notion is careless, for F sharp does in fact depend on n. In fact, there's one such F sharp for every n greater or equal to 0. This is much like our abuse of D in the exterior derivative, right? There's not just one exterior derivative. But it sounds so much cooler if you say there's one exterior derivative that does the gradient, curl, and divergence. Like if you say, well, there's a common concept of exterior derivative and different levels of it do different things, it's less impressive. I much prefer to just drop it's just D, right? It helps sell it.
Yeah.
Sort of like in category theory, how you use the generalized the.
The generalized the?
Yeah, instead of the meaning a particular object, in category theory, sometimes it means a particular object
What?
up to isomorphism
What?
by unique isomorphism.
What
So it's
is-
a lot easier to say the.
Oh.
So you can say
The complex numbers?
the initial object in the
Oh.
category of sets. Or wait,
What is the meaning of is in category theory?
is. Depends on what your definition of is.
Maybe I should vote for Clinton. Sorry. That's too dated a reference, I'm sorry. Goodness gracious, I stand by my comment. If you have questions about category theory, ask Nathan Bedell. It's here. Where was I? Huh. So the has a you guys have given the a technical meaning in category theory?
Yeah, it's generalized the.
Gosh. Oh, I'm
You
gonna
can
go
look up
crazy.
the article on the NCAT lab.
Oh my goodness gracious. What's this world coming to? Alright. I mean, that's cool. Ba-dum. Oh, yes, my lemma. Are either of you familiar with Strong Bad?
Yes.
Sounds really familiar.
And like the Trogdor, the Burninator, and all that?
Yeah.
It's my dream to have been in that like presidential debate the other night and just to have shouted at the top of my lungs, my emails! My emails! My emails! If you understand that reference.
Yeah.
Yeah. I called my brother up. I'm like, at this point, I stand up and I yell that. Bill was amused because we used to watch that. It's been a while since I checked out that website. Is it down?
I think, well, they like went on a hiatus for
Oh, okay.
the longest time, but I think recently they put some new stuff.
That was fun. Yeah, Trogdor was like really big for some point in my undergraduate. He's like, people were drawing Trogdors in chalk all over the brickyard and stuff. You'd see awkward one muscled arm dragons chalked in here and there and
Yeah, what was
everywhere.
that like?
Burninating the countryside, burninating the people. Let's see here. Trogdor. I don't know why you guys keep distracting me with all this stuff. So partial, this is the lemma, eh?
Yeah.
So in particular, we've got this commutative diagram. So we have the singular end chains, and then the boundary operator is unlike the exterior derivative. It goes to the degree less things, right? So it's more like that co-derivative we talked about a bit. Uh-oh. I feel a category theoretic comment coming on. Let's see here. S and minus 1.
You just reverse the arrows, it's not that difficult.
Oh, okay. Isn't that essentially what Trump is saying? You just undo what you guys have been doing, and then everything will grow like Topsy. So here. All right. Let's see here. Look at the proof. So let's see here. I'm trying to show F sharp. Let's see, where should I start with this? F sharp, and then wait a minute. Sense? Oh, I think it's the. This is also F sharp, isn't it?
Yeah, but different F sharp.
This is the careless notation having its way with me, isn't it? All right, so you're basically trying to show like this is the same as that, right? So a typical thing in here is the sum. Wait a minute. If I prove this on a. Do I need to do it for a sum? I guess I'll do it for a sum. So there's my typical element in here, right? I want to feed it to the boundary operator, right? And then I want to fit the sharp of that. How's that go? Ah, yes. So our definition of boundary operator was sum over I minus 1 to the I, the M. Oh, he has the good sense to not do this on, I'm making this more complicated than it needs to be. If we can prove this on the basis, then we extend linearly, right? So let me not be a Neanderthal, and sorry, I'm a Trump supporter, so it shows up in weird ways. Sorry, I'm working Trump into all my classes right now. It's my it's going to make these lectures very dated.
Yeah.
And unnecessarily controversial. But let's see here. So so that's F sharp. Let's see here. I don't know, like it'd be really different if he wins versus if he loses, right? Let's see here. So that's sigma. Is the epsilon come before or after? I forgot.
Okay.
After, right? So that takes your face and does what to it? Deletes a side or something? Or no? What do these things do? They delete the ith face, right? So that takes it and changes it from like an n simplex to an n minus 1 simplex in a canonical oriented way. All right, and then using the definition of extending linearly, we pull the sum out, pull these integers out, and so then I have f of sigma. What can I do? Do I have to leave the epsilon I in there? I guess I do. All right. I forgot what I'm trying to do. It's not a good time.
Commutes. So you do the
What commutes?
boundary and F sharp.
Oh, you think we would meet in the middle on this one?
Yeah, that's what he does.
Okay. So you can't see what to do from here? It's hopeless.
I mean, I think you could.
But if, well, we'll trust the master. Let's go the other way. So, n-1 boundary, yeah? No,
No, it's always the end boundary.
it's always n boundary, alright. Different sharp, but careless we shall be. So this is the n boundary of f composed with sigma. And so that is equal to the sum. Oh, okay. Oh, wow. Yeah.
Yeah,
I'm sorry.
essentially it just uses function.
I'm so sorry I took so long.
Function associativity.
I'm sorry I took so long to prove this, guys. I'm an idiot. Let's see here. And then this is the same as, yeah, what you said, Nathan. I mean, this is actually also a composition if you want me to be
Yeah.
more pedantic about it, yeah. Okay. And then we extend linearly across the n chains, and that gives us to it, gives it to us. Okay, so next, lemma 4.9. Lemma 4.9 say. Says the continuous function, the homomorphic image of the n cycles of x are a subset of the n cycles of y. And the inverse image of the n cycles of y, well, I don't know what it's, maybe I'll state it as it's stated. Think about what this means for inverse images in just a second here. So f sharp of the boundaries of x is a subset of the boundaries of y. Let's see what that's, well, can I take inverse image here? I guess I can, right? If you want. I don't know if that's interesting or not, but so the, well anyway, it says what it says. So the image of the boundaries is a subset of the boundaries, the image of the cycles, subset of the cycles. Yeah, I should just leave it as is. Yeah, it's good. Alright. So proof. Let's see here. So let sigma be an element of the n cycle. Again, we'll extend linearly, so if we do it on the basis, we're good. So we let the sigma be an element of the be an n cycle in x, right? And if we look at, so that means what? The n boundary acting on sigma is equal to 0, right? It's in the kernel of that. So if we look at the boundary of f of sigma, right?
F sharp, right?
Yeah, I'm sorry. Fair enough. I want to show that that is also 0.
So you can use the lemma and show that it can use.
So this is just using the lemma f sharp. Very good, very good. So that's f sharp of,
Boundary of sigma.
sorry, I can't make up my mind whether I want to write composites or, you know. Okay, so that's f sharp of 0, but f being a homomorphism, f 0 to 0, bam. So that of course says that f sharp of sigma is an element of the cycles of y. So that's the first part of lemma 4.9. Let gamma be an element of the boundary and boundary of X. Hence, there exists a sigma. Maybe I should say sigma. Let me say sigma is in the boundary of X. So there exists a gamma for which what?
Sigma is equal to the boundary of gamma.
Right, so the n minus n plus 1?
Yeah.
Gamma equals to sigma. And again, it's going to be a lemma, right? So we look at f sharp
Sigma.
of sigma, which is, of course, f sharp of the n plus 1 boundary of gamma. Commute them by the lemma. And recognize that this is a particular what's the word? N chain? No. Dang it. N chain and you know what? This is an element of Sn plus 1
Yeah.
of y. Right? So then we have that this guy is the image under the n plus 1 map of that, which is tantamount to saying that visibly sigma is, well, excuse me, f sharp of sigma, right, is an n boundary of y. These are fun. Alright, this has to stop. Theorem 4.10. Theorem 4.10 say? It says that Hn is a functor from the category of topological spaces to the category of abelian groups. Right? This is a functor. So I guess that means it's entitled to all the rights and privileges therein too. So what? What is our burden of proof?
Show that the induced mapping has the required properties.
Alright, so you guys help me out here. We need to do, so he says we've already defined Hn on objects. Oh, right, last time, what did we say? On objects, Hn of x was what? Equals to
Zn of x mod Bn of x.
right, so this gives us a way of associating for each topological object a corresponding abelian group, right? But a functor does two things. It associates objects to objects, but also morphisms to morphisms in the natural way, right? So, okay. And so the let's see here, HNF, what is this? HNF goes from HN HNY. How so? Tell me more. He says what we're going to do is, and this is of course for, we're starting with the topological morphism, a continuous function, right? Trying to describe the corresponding morphism of abelian groups, right? And that corresponding morphism is given as follows. You take Zn plus Bn of x, all right? And you map it to f sharp, right, of Zn plus the n boundary of y. In other words, let's see here, in the class notation, we're taking the class, oh man, I erased that stupid thing. What is this? This is the class of Zn, right? And we're mapping it to the class of what?
F sharp with
F sharp of the F sharp of Zn. So that's the morphism. Oh, that's what it does. Okay, he says, okay, first of all, by lemma 4.9, we have that if Zn is a cycle, then this guy is a cycle.
we just proved.
You just proved that, yeah. What else? This is independent of the choice of representative, right? Because, why is that?
He explains this if you use a different representative.
Mm-hmm.
If you use like Zn plus some Bn.
So let's say, yeah, this hypothetically, suppose we have f of Zn plus Bn, right?
Plus.
So this would be f sharp of, say, Zn prime, a different representative. Suppose that Zn and Zn prime are elements of the same homology class, right? Like that. Then Zn prime is equal to Zn plus some boundary. But this is a homomorphism, right? And this,
So the class of that is going to be.
right. So this is, right, exactly. So the class of the prime one is the class of the unprimed one, because when you take the class, I mean, class doesn't care about this because class is a coset built by boundaries. So if you had a boundary term, it just gets sucked into there, basically. And the reason I know that that is a boundary term is because of lemma 4.9. The image of a boundary is a boundary, right? So this is in BNY. Does that make sense? Mm-hmm. Okay. What else? So that means that at least the morphism is well defined, right? We need to check that the identity goes to the identity and the composition. Let's see here. So I guess that would be the identity from x to x, is that right? This is the identity. The identity of the in the topological category is just the identity mapping on the space. I mean, yeah, I think that's just kind of like pretty obvious from the constructions that the identity is the identity, because basically you're just composing with f, right? So when f becomes the identity, these just become just chains to chains, the same chains. Now the composition thing, so the other one was what? That hn of gf. I mean, I'd like to think about that for just a minute. G and f is equal to hn g hn f, right? Let's see, so this would be based on doing what, like gf sharps of stuff, right? This would be something like so that would be G sharp, something like G sharp composed with F sharp, I guess. So we for G composed with F to make sense, we have to have something like X to Y to Z, right? So the first one being F, the second one being G, and I don't know. I personally would have to do a little more writing before I was convinced, but let me just sit down and look at it for a second.
Yeah, I mean, we could just go through it.
What's that?
We could just go through it and show.
Okay. Probably a good idea. Anyway, it's an idea. Okay, so it's probably easier to start over here, right? So we feed. No, I'm saying if that's the right idea. I need to look at a. I should look at a class. I'm supposed to look at classes of cycles where. I mean, I should be looking at hn of z, hn of y, right? Other way around, right? Sorry. And so this would be allegedly the F sharp, right? This is the G sharp. Is that right? I mean, specifically,
Yeah.
we have F sharp of the class of the n cycle with representative Zn, right? Class with representative Zn is equal to the class of, what is it? Oh, that's not how to say it. The thing is, I haven't given a stupid name to this. I'm getting confused by my own notation. I'm an idiot. This is Hn, right?
Right.
And I probably should put a little. I mean, I don't know. There's different HNs going on here, right? I mean, I've got Hn of class Zn is equal to the class of F sharp Zn, right? Which is an element of HNY. But I also have the Hn of, say, the class of, I need something else, Wn, let's say, is the class of G sharp of Wn, right? And that would be an element of Hnz. The notation's a little bit confusing. I mean, he's using Hn in two different ways, right? On the one hand, it's the homology group. On the other hand, it's the functor.
Yeah. Later he uses like F star. To
Oh,
show
so I should say F. So this
like
is
F star of the class.
Thank you. That's helpful. Let's get in the habit of doing that then. So this is the class of F sharp. Is that right?
Mm-hmm.
Okay. And G star of the class of Wn is equal to the class of G sharp. So what we really want to look at is G star of F star, right? Unlike the class of Zn. So that would be G star of the class of F sharp of Zn, which would then be the class of G sharp, F sharp of Zn.
It's 3:00 p.m.
Oh, quiet. I don't know.
I guess we would need to show that like G sharp F sharp is G F sharp.
Right, so yeah, exactly. We need G sharp F sharp is equal to G F sharp. That's exactly what it boils down to. Right. But that's pretty easy because G F sharp acting on sigma, right, is equal to G F sigma, which is of course G F sigma, which is,
G F sharp sigma.
yeah, it's G sharp of F sharp sigma. In other words, it's G sharp composed with F sharp sigma. Yeah. It is as he says. They're easy consequences of the definition. Yeah. Yeah. As long as you don't get hung up in some sort of notational quagmire like I was working on. Let's see here.
Yeah, like you should have wrote Hn of F of the class of Zn.
Oh, thank you,
Right,
Nathan.
yeah.
That's
Or Hn of G.
That's what I was missing. So this is a F, this is G. Then it makes sense. Right. So I was gonna adorn it with an upper F and an upper G because I'm an idiot. Categorically speaking. Alright, where are we? We have functors. Corollary. If x and y are homeomorphic, alright, then they have the same homology groups. So, homeomorphic spaces share the same homological data, I suppose. At least singular homology. That's all we've done so far. Proof theorem 0.5, which was what?
Yeah, it's that functors map equivalences to equivalences.
Ah, okay. So again, if we have homeomorphic topological spaces, we have isomorphic homology groups. Right. So I suppose if you have your favorite, sort of archetypical abelian group, then you could say they're equal if you want, I guess. But isomorphic just to be safe. If you're different. Anyway, important and related, the definition. Put it over here. The rank of Hn of x is equal to, oh, he doesn't give a notation to it, but that is known as the Betti number of x. So, what does he say about that? He says if Hn is free abelian, then it's characterized by its rank. Otherwise, there's more information in the homology group. So free abelian basically just means that Hn is just straight up some Cartesian product of the integers. So the rank is just the number of those, and that's it in terms of group theory. There's nothing like, is it like Z cross Z one way, or is it Z cross Z the other way? No, it's just Z cross Z. The Betti number is 2, end of story. On the other hand, if you have Z cross Z and then some torsion piece, then all kinds of wacky wild stuff can happen with the torsion piece. There's more that torsion piece doesn't get picked up in the rank, right? The rank just concerns the torsionless part, if I remember right. Anyway, as he said, if it's free abelian characterized by rank, otherwise you got more information in the homology group. I actually talked about this paragraph last class. So here's a dimension. It starts out kind of small. We'll take it though. Theorem. 4.12. So the next paragraph in the book, of course, he discusses how this is singular homology. It's theoretically pure. It's nice. It's easy to relatively easy to prove things, but it's a little bit divorced from geometry. Later, we prove that following Eilenberg and what was his name? Oh man, I forgot.
Steenrod.
Steenrod, yeah, the Steenrod-Eilenberg axioms that these different methods of calculating homology are equivalent in as much as they overlap. You can't actually triangulate all spaces, so we have to compare where they match up. I think the singular homology allows for things that the more geometric techniques are a little bit incapable of, slapping triangles on.
Yeah,
All right,
I don't think you can triangulize the real projective plane.
Yeah, well, I forget, but that sounds reasonable. See, your dimension axiom. Wait a minute, how is this a theorem? Oh no! Alright. If X is a one-point space, did somebody actually publish this in a paper? One-point space, then I could see the referee rejecting it. Like, this is too simple. Oh, sorry. Hn(x) is equal to 0 for all n greater than 0.
Isn't this actually one of the Eilenberg-Steenrod axioms, though? It's like it comes in a set, right?
Ah. Yeah, I don't remember. But it's been a little bit since I got into those. But that seems. I know it's like when you look at axioms of set theory. There's some axioms in there that make you go, what? Like, what was the one? Something about elements in a set.
Comprehension?
Comprehension. How's that go?
Essentially says that if you have some proposition, then there is a set whose members are exactly those that satisfy the proposition.
Ah. Okay. I'm not sure that was one I was thinking of, but. Oh, okay, so what's the proof of this? I'm not going to write anything, I'm just going to read. It says, for each n greater than or equal to 0, there's only one singular n simplex, the constant map. Alright? So, the Sn of x basically is just what? Where what? That's the constant map. And so the infinite cyclic group generated by sigma n, if you calculate the boundary operator, what do you get? Fine, I'll write partial n sigma n equals to, oh goodness gracious, sum n equals 0 to n minus 1 to the I sigma n epsilon, the phase map. What is that?
Since sigma n epsilon I is going to be an n minus 1 simplex, and there's only one n minus 1 simplex.
So that's exactly, that is just minus 1 to the I sigma n minus 1 then, right? course, you can then, since that's constant, I mean, it's the same thing, and this is like a summation over, factor it out of the sum, basically, right? And he says it follows that the boundary of n, sigma n, is equal to what? So this is like 1 minus 1 plus 1 minus 1, right? So how's it go? 0 for n odd, right? And it's sigma n minus 1 for n even. So the boundary map is 0 when n is odd, and the boundary map is an isomorphism when n is even. So let's see here. Let's look at the singular n change, n plus 1x, n minus 1x. So we have boundary n plus 1, boundary n. And then I think we just, we look at even and odd cases and we argue that all the homology groups are 0. Either because of the injectivity, for one reason or the other. Let's suppose n is even, all right? So Sn x is what? If n is even, then we have what? Partial n plus 1 is what?
0.
That's 0, right? And let's see here, on the other hand, partial n is what? It's isomorphism, right? Right. More to the point, it's injective, right? We just say it's injective. So, when we calculate the homology, right, which is what? It's the kernel of the n boundary divided by the modulo, I should say, the image of the n plus 1 boundary, is that right? So I got that right, the counting. Right? So, that's 0. And yes, 0 over 0 is 0 in this context. It's no problem. And then, in the case that it's odd, what happens? If it's odd, then this is 1 to 1, and this one is the 0 map, right? And so then you get hn of x looks like, let's see here, that's the 0 map, right? So that being the 0 map, what's the kernel? Well, the kernel is Sn of x, right? Oh, this is cool.
Yeah, and we need the partial n plus 1 is onto, not 1 to 1.
Yeah, right. Yeah, this time the last time it was the 1 to 1 gave me kernel 0.
Yeah.
This time you're right. It's that it's onto is the map. The point is the stupid identity map. So, but yeah, the fact that it's onto is really what I need because then the image
It's going to be Sn.
is Sn. Yeah. So it's kind of funny. So that's 0. So both of the extreme quotient cases are both. I mean that's kind of fun algebraically what goes on here. Yeah. Cool.
What's the point?
What's that?
But what's the point?
Oh. The point is if x is a one-point space, then the homology is 0 for all n. Yes. I don't know why you'd study one-point spaces, but
Actually, the answer...
it almost seems pointless. It's not quite, though.
See what she did say.
The answer,
You knew that was... I mean, you knew I've been waiting to work that in one way or another. I mean, I'm bound and determined to do that.
I think the answer is corollary 4.25.
Corollary 4.25. If X is contractible, then yes, that is a good point, Nathan. So the connection of one-point spaces to contractible spaces is what makes it interesting. That's a good point. It is a good point, yes. I stand by that. Unintentional pun. Let's see here. All right. He says a space is acyclic if the homology is 0 for all n greater than or equal to 1. So the dimension axiom shows that. Oh, you're right. That has to be the like the Steenrod axioms later. Steenrod, right? Steenrod. Yeah. See, I'm an idiot. All right. So the next thing in here, the set of path components. If we look at the path components of X, then the homology is a direct sum over the homologies of the path components. This is very cool result. Write that down. So if we have X is like a union over lambda of X lambda, these are the path components, right? As we talked about before, then the homology of X is actually the direct sum over lambda of the homologies of these guys. Of course, he writes it, and it's probably better. I don't know, whatever. He writes that like this, but he means direct sum, of course. Yeah. Now, basically the proof is that if you look at a, gamma, look at an n cycle, weird. All of a sudden now he's got an I on there. It's not his notation before. What's he up to? Oh. Basically he's kind of building what he's about to say into the notation. I believe the idea is that the sigma I is like an element of is that the right thing to say? The image of it, rather, right? Is an element of X lambda for some particular lambda. So like, well, I guess it's clear enough, right? If you think about a general n chain, right, which would be something like, we just think about sigma. It's a mapping from delta n, right, into X. So if X has different pieces, right, then what he's saying, among other things, is that, and here's just a cheating picture of it, this could be the image of sigma, this could be the actual image of sigma. And so if you look at that, you can...
I think you can argue it has to be in the same path component because it's continuous.
Oh, because the continuous image of a connected set is connected?
Yeah.
But my picture is impossible.
Yeah.
So it has to be like that or something. Yeah. Cool. Well, that's better. That's easier to think about. Where was I? So think there's anything, once you have that under control, I don't think there's anything particularly difficult here. So what's he say? So basically, if I take an n chain in here, right, it's a formal linear combination, integer linear combination of things, but at the level of the things being added, each one of those has to fit into just one of these by the continuity of the singular n simplices. And so you can arrange them basically to fit. I mean, there's a natural. If you take an n chain here, you can build it as a sum of n chains in this one, you know, in the different components. And so that's how I get. That is the isomorphism, right? The isomorphism is you take the n chain in here and you split it into the subchains that fit into each of the path components. And then basically all he does argue here is that that's an invertible thing, right? Yeah, I don't think I'm going to write that out. Any questions? Or? Of course, this is like really, really fun for examples, right? Because if you have, I mean, if you do something like calculate the homology of a space, right? And then you just take that space and form a disjoint union with itself, then this tells you that the homology is the direct product of the direct sum of the two, which is kind of fun, you know. So what's the so I guess if you take a circle, I mean we'll find the homology. Well, eventually we'll find the homology of the circle. This would allow us to do like the disjoint. If we did like disjoint union of two circles, it would be, you know, the direct sum of z with z, I guess. I guess it's not too exciting. It's moderately exciting, whatever. You choose your excitement level on this one. I won't force it on you. Where are we? All right, so theorem, oh, goodness gracious. Theorem 4.14. If X is a non-empty path-connected space, then the zeroth homology is the integers. Moreover, if you have 2 points in X, then the class of X naught is equal to the class of X1. Any of those, that they're all generators for the zeroth homology, right? So the class of any point serves as the generator of the zeroth homology. Point 2, for any space X, the group, the zeroth homology, is your H0X, is free abelian of rank the cardinality of lambda, where lambda is the index set of the path components. So like in my stupid discussion we just had a second ago, lambda would be 1, 2. And the cardinality would have been 2 if we took a disjoint union of a circle with a circle, for example. So basically the rank of the zeroth homology just counts the number of path components. That's what it's for. Which is what we saw before with what? The fundamental, like pi naught?
Pi naught, yeah.
Pi naught's the same thing,
This
right?
gives you a number, this gives you...
It's almost like there's some kind of connection between homotopy and homology.
Crazy.
Alright, in the interest of getting to that next time, let me continue reading this so we can start at the, hopefully next time we'll start at the homotopy axiom. Let's see here. Point 3, if x and y are path-connected spaces and you have a continuous function from x to y, then the f star